Hello, welcome to Buffers Lesson 1, Video 2. In the last video, we talked about what is a buffer system, the common ion effect, and we looked at an example of a weak acid soluble salt of the acid buffer system. So now we're going to look at our example problem and derive something called the Henderson-Hasselbalch equation. So our example problem says, calculate the H3O plus concentration and pH of a buffer solution made from 0.100 molar acetic acid and 0.200 molar sodium acetate. So using our criteria to make sure that this is a buffer system, we do have a weak acid. We know it's a weak acid. It's acetic acid. It does have a Ka value. And we have sodium acetate, which is a soluble salt, and we have a common ion, acetate, from both of these from our previous example up here. Concentrations are reasonably similar. So it's always best to start with an equation. So we actually have two of them. So our NaC2H3O2 is 100% soluble. So we get our two ions. So we need to get the concentration of especially our acetate because that's our common ion. So this is 0.200 molar and we have a single arrow going over. We know that this is going to go to 0 and these two are going to go to 0.200 molar apiece. But the only one we're really interested in is the acetate. So whatever the concentration of the salt is, that's going to be the concentration of the common ion. We also have our equilibrium system. This one is going to require an ice chart. So with this one, our ice chart, our initial concentration of this is 0.100 molar. These two are 0. And this is just a straight ice chart like we've been doing all year. Now, if we want to solve for H3O+, we know that we're going to have to go through and find a Ka, which we can look up, and it's 1.8 times 10 to the negative fifth. Use your reference sheet that you should have. If you do not have one, let me know, and I can email you a picture of one. And we know that that Ka value is equal to the concentration of H3O+, which is X, times the concentration of C2H3O2-, which is X, all over the concentration of the acetic acid. And all of these are equilibrium, so we use our E values. So now that we have this equation, we can make our assumption. This is times 10 to the negative 1, this is times 10 to the negative fifth, so we can ignore and assume that this X is not going to affect the value, which makes our life a lot easier. So if we assume and we calculate this out, and I'm not going to go through the calculation, you can do that. You should get 9.00 times 10 to the negative 6 for our X value, which means that our concentration of H3O+ is equal to that, 9.00 times 10 to the negative 6 molar. And if we take the negative log of that, we can get the pH to be 5.05. So, not too bad. But if these were not, if we could not assume, we'd have to go through the quadratic formula, which we all know is a little bit more tedious. So, based on this information about being able to assume, someone a lot smarter than me came up with an equation called the Henderson-Hasselbalch equation, and I imagine that their last names are Henderson and Hasselbalch. So, to derive this equation, you're not responsible for the derivation, but it goes to show where this information came from. If this is our generic equation for a weak acid, and we know that Ka is equal to the concentration of H3O+ times the concentration of our salt, which is the A-, all over HA. And we know that this right here, the salt ion, the soluble salt, adds to this. So if we were to go ahead and solve this equation right here for H3O plus, we would get H3O plus is equal to Ka times the concentration of HA over our concentration of the salt. If we take the log of both sides of this, we would get the log of H3O plus is equal to the log of Ka times the log of HA over salt. And if we took the inverse of that, we get the negative log of H3O plus is equal to the negative log of Ka plus the log of the salt concentration over HA. So, negative log of H3O plus, that should look familiar. That's pH. Negative log Ka, we've talked about this before. That's pKa. That's why we talked about it. Plus the log of the salt concentration over concentration of HA. This is the equation that we can use now without having to go through an ice chart. We just need to know the concentration of the salt. So, using our previous example that we already did, we know that we had 0.100 molar HC2H3O2 and 0.200 molar NaC2H3O2. So this is our HA and this is our salt. Our Ka value, 1.8 times 10 to the negative fifth. Well, if we take the negative log of that number, we get pKa. So that gives us 4.74. So we have all of our pieces. If we want to find pH, we use the Henderson-Hasselbalch equation. So the pKa, 4.74, plus the log of the salt concentration, 0.200, over the acid concentration, the HA. And lo and behold, we get 5.04. Guess what? That's almost exactly the same number as we got before. There's a margin of error, which is acceptable. So go ahead and try our next, well, the next example will be in the next video. That's for weak bases plus salts of the weak base.